Academy, where numbers and variables actually meet past three. Today we are going to be looking at another section, Bernoulli's equation. Yes, that is first order differential equation. Now remember in our previous class on linear equation, yes, we actually mentioned that equations of the form the y all over the x plus py is equal to q, where p and q are both functions of x. Yes, they are both functions of x, can be analyzed using the integrating factor. And we actually concluded that to get the equation, we just have to multiply y times the integrating factor is equal to integral q times integrating factor, then here we have dx. Yes, that's for linear differential equations. That is first order differential equations. Now today we are going to be looking at equations in this form, where we have the y all over the x plus py is equal to q y raised to the power of n. Yes, so this is a Bernoulli equation. Yes, this is a Bernoulli equation. Yes, and of course, Bernoulli's equation has vast applications in engineering, fluid mechanics, and so on. So today, we are going to be seeing how to analyze an equation of this form, Bernoulli's equation, where q has a coefficient y raised to the power of n. Now, in this case, to analyze this equation, the first step is to divide. Yes, is to divide through by the coefficient of q. Yes, and as you can see here, the coefficient of q is y raised to the power of n. So it means we are dividing both the left-hand side and the right-hand side by y raised to the power of n. So it therefore means that here we have 1 all over y raised to the power of n, the y all over the x, plus, here we have py all over y raised to the power of n, will be equal to, we have qy raised to the power of n, all over y raised to the power of n. Yes, all over y raised to the power of n. Now looking at this is the same as saying y raised to the power of minus n. Yes, 1 all over y power n is the same thing as y raised to the power of minus n. Then here we have the y all over the x plus, here, this will be p y raised to the power of 1 minus n. Yes, remember in indices, we said m raised to the power of x divided by m raised to the power of y is m raised to the power of x minus y. Yes, because the bases here are equal, so we are subtracting the powers. Now here we have this y here, the same thing as y raised to the power of 1. Yes, the same thing as y raised to the power of 1. So we have y power 1 minus n. Now it's equal to, those y power n will go with y power n. And here will be left with q. Yes, we'll be left with q. So at this point, let z be equal to y raised to the power of 1 minus n. Yes, that is the coefficient of p. So if z is equal to y raised to the power of 1 minus n, it therefore means that the z all over the x will be equal to, here we have 1 minus n, y raised to the power of 1 minus n, then here we have the y all over the x. Yes, the y all over the x. So it means here, if the z all over the x is equal to 1 minus n, y raised to the power of, now remember here, we actually subtracting 1 from the power. So here we have minus 1, then before the y all over the x. Yes, because it is an implicit function. So of course, this will be equal to 1 minus y, 1 minus n, y raised to the power of 1 minus n minus 1. Then here we have the y all over dx. So it means the z all over dx will be equal to 1 minus n y raised to the power of minus n. Yes, because those 1 minus 1 will go, I'll be left with minus n there. Now the y all over dx. The y all over dx. Please, let's take note of this. Yes, so the z is 1 minus n y raised to the power of minus n, the y all over dx. Now let's tag these equations. Let's call the first one here, this Bernoulli's equation, equation 1. Yes, let's call it equation 1. And let's also call this equation here equation 2. Yes, equation 2. So at this point, now we want to make this equation 2. Yes, we want to make this y raised to the power of minus n the y dx to be the z all over dx. So it means we're going to multiply. We're going to multiply equation 2. Yes, we're going to multiply equation 2 by 1 minus n. Yes, that's 1 minus n. So if we're multiplying equation 2 by 1 minus n, it means this very equation now will be, we have 1 minus n. Yes, 1 minus n. Then we have y raised to the power of minus n. The y all over dx. Yes, the y all over dx plus. Here we have 1 minus n. Then here we have p y raised to the power of 1 minus n is equal to, we have q. We have 1 minus n q. Yes, 1 minus n q. Now we can call this equation equation 3. Now at this point, looking at this function here, we discover that it's the same thing as the z all over dx. The whole of this is the z all over dx. So it means here we have the z all over dx. Yes, the z all over dx plus, here we have 1 minus n. Then here we have p raised to the power of 1 minus n. Yes, raised to the power of 1 minus n. Yes, y raised to the power of 1 minus n. Then here we have this to be equal to 1 minus n. Then here we have q. Yes, we have q. So at this point, let p1, yes, let p1 be equal to 1 minus n times p. And q1 be equal to 1 minus n q. So it therefore means that here, what we're going to have here now will be, yes, so we're going to have here to be the y, the z all over dx plus, so remember 1 minus n times p is now our p1. So we have p1, yes, then y raised to the power of 1 minus n. Now the whole of this will be equal to q1. Yes, it will be equal to q1. So at this point, let's call this equation, let's call this equation 4. Yes, so here, now let's compare. Comparing equation 4 with, yes, equation 4 with the first one. Let's call this equation star. Yes, let's call this equation star. So in comparing the both of them, that is equation star, it means that here we have z. Now this will be z times the integrating factor. Integrating factor will be equal to, then here we have integral, we have q1 times integrating factor, then we have dx. Yes, so z times integrating factor is equal to integral q1 times integrating factor dx. So now we're going to solve some examples now. Now let's look at example 1. Now example 1. Now example 1, we have to solve. Yes, solve the y all over dx. The y all over dx plus y tan x. Y tan x is equal to, we have y raised to the power of 3. Y raised to the power of 3 sec power 4x. Yes, sec power 4x. So it means in this case, Now solution. Yes, now this is a Bernoulli's equation. Yes, it's a Bernoulli's equation in the sense that the function of x here has the coefficients y raised to the power of 3, just like this case where you have y raised to the power of n. So it means in this case, the first thing to do is to divide all through by the coefficient of sec power 4 x. So here we're going to divide through by y raised to the power of 3. Yes, just like the way we divided through by y raised to the power of n. So here we are dividing through by y raised to the power of 3. It means in this case, we are going to have 1 all over y raised to the power of 3. We have the y all over the x plus we have y all over y raised to the power of 3. We have tan x is equal to y raised to the power of 3 sec 4x all over y raised to the power of 3. Yes, all over y raised to the power of 3. Now looking at this is the same thing as saying y raised to the power of minus 3, the y all over the x, plus, here we have y raised to the power of minus 2. Yes, because y all over y power 3 is 1 all over y power 2, because this y here, y we're going to this y square times. Okay, so here we have tan x is equal to this, we'll go with this. So we left is sec power 4x. Yes, sec power 4x. So at this point, let z be equal to y raised to the power of minus 2. Yes, let z be equal to y raised to the power of minus 2. So it means here, the z all over the x, will be equal to, when you differentiate this, we have minus 2y raised to the power of minus 3. Then we have the y all over the x. Yes, the y all over the x. Now, if you look at this now, please, let's take note of this. Yes, so here we have the z all over the x. Now, remember, we want to change this to the z all over the x. Now, to change this, you can see that the whole of this here, what we need to multiply by this to change it to the z all over the x is minus 2. Yes, it's this minus 2. So here now, we're going to multiply through. Yes, multiply through by minus 2. Yes, multiply through by minus 2. Now, if we're multiplying through by minus 2, or let's start this and let's call this equation 2. Yes, let's call this equation 2. Let's call this equation 1. Yes, let's call this equation 1. And here we have equation 2. So here, we just have to multiply equation 2 by minus 2. Yes, multiply equation 2 by minus 2. It means when you're multiplying through by minus 2, that's equation 2. We have minus 2, y raised to the power of minus 3, the y all over the x. Then here we have minus. This is plus. So plus times minus 2. That will give us minus 2, y raised to the power of minus 2. Then here we have tan x is equal to minus 2. Then we have sec power 4x. Yes. Now looking at this very closely, you'll discover that the whole of this now is that this particular function here is the same thing as the z all over the x. Yes, the z all over the x. So it therefore implies that here we have the z all over the x. That's for this. Minus. Now remember we said, take note of this. Yes, take note of this. Let me call this, let me just asterisk this. So now remember we said let z be equal to y raised to the power of minus 2. Yes, so it therefore means that here we have minus 2. This is z now. We have z. Then here we have tan x is equal to minus 2 sec power 4x. Yes. So now the next step is to look for the integrating factor. Yes. To look for the integrating factor. Now remember we said the equation now will be z times the integrating factor is equal to integral. we have q times the integrating factor, then we have the x. Yes, so now let's see the integrating factor. Now remember our integrating factor. Yes, in our class on linear differential equation, we mentioned that the integrating factor is e raised to the power of integral p dx. Yes, now our p now from this equation, our p is minus 2 tan x. Minus 2 tan x. Yes, that's the coefficient of z. Minus 2 tan x. Then our q, and the value of q is minus 2 sec power 4 x. Yes, that's the value of our q. Now let's see integral this now. So integral p dx will be equal to integral minus 2 tan x, and here we have the x. And this is the same minus 2 outside, integral, here we have tan x dx. Okay, so now the whole of this now will be minus 2 integral. Now remember, tan x is the same thing as sine x all over cos x. So here we have sine x all over cos x. Then here we have dx. So when you integrate this, it will give minus 2 in bracket. The integral of this is minus ln cos x. Yes, so it means that will give us minus 2 times minus ln cos x. It becomes 2 ln cos x. Yes, 2 ln cos x. 2 ln cos x. And of course, we all know that here, now let me bring this sine x, the integral of sine x all over cos x. Let me bring it out. Yes, so that you don't get confused. The integral of sine x all over cos x. So when you integrate sine x all over cos x dx. Now at this point, let u be equal to cos x. So that the u all over the x will be equal to minus sine x. The u will be equal to minus sine x dx. And the x will be equal to minus, we have the u all over sine x. Or let me put the minus here. The u all over minus sine x. So it means the whole of this integral sine x all over cos x dx will be equal to integral, we have sine x all over. Now remember we said let u be equal to cos x. So here we have u, and the value of our dx is the u all over minus sine x. So the whole of this will go with this. So remember we have minus there, so it will be minus integral 1 all over u du. And when you integrate 1 over u, it gives you ln u. Yes, ln u. So here it means we have minus ln, the value of our u, remember we say let u be equal to cos x. So we have cos x. So that's how we actually got this value. Yes, that's how we got this minus ln cos x. Now this minus, to see it here. So that will give us minus times minus is plus. So we have 2 ln cos x. And this is the same thing as saying ln cos x all squared. Yes, ln cos x all squared. So now it means that here the integrating factor, yes, the integrating factor if, the integrating factor will be equal to e integral p dx. That will be e integral, and already we have the value of p dx, integral p dx. That actually gave us ln cos x squared. So here we have ln cos x all squared. So it means the whole of this now will be e raised to the power of log. We have cos x all squared, then this e. So that will give us cos x all squared. And of course, cos x all squared is the same thing as cos squared x. So here we have cos square x. Now this is the integrating factor. Yes, this is the integrating factor. So coming back to the equation, remember we said z times integrating factor is equal to integral we have q times integrating factor, then here we have the x. It means now we have z times the integrating factor is cos squared x. Yes, the integrating factor is cos squared x. Now we have z times cos squared x will be equal to integral. We have q. So the value of our q, now let's look at it from here. We said the value of our q is sec power 4x. Yes, sec power 4x. That's the value of our q. Yes. Now remember we pick the value of p. Yes, look at it here. We got this as the value of our p and this the value of our q. So it means the value of q here is minus 2 sec power 4x. Then the integrating factor is cos squared x. Then here we have the x. So it means z cos squared x will be equal to, so here, this is the same thing as saying minus 2 integral. So the whole of this now will be sec power 4x. Then here we have cos squared x dx. So it means the whole of the right hand side will be minus 2 integral. Now sec. Now remember we say sec x is 1 all over cos x. So it means sec power 4x will be 1 all over cos power 4x. So here we have 1 all over cos power 4x. Then here we have cos squared x, then dx. Yes, so this cos squared x will cancel this. So here you'll be left with cos squared x. Yes, we'll be left with cos squared x. Now, it means that here, yes, it means we're integrating this now. So here we have z cos squared x, the left hand side, is equal to minus 2 integral. Here now we have 1 all over cos squared x. 1 all over cos squared x. So here we have the x. So now this is the same as saying minus 2 integral sec square x. Then here we have the x. So it means z cos square x will be equal to minus 2. Now when you integrate sec square x, it gives tan x. So here we have tan x. Yes, remember when you differentiate tan x, it gives sec square x. It therefore implies that when you integrate sec square x, it gives tan x. Because integration is actually the reverse aspect of differentiation. So here we have plus constant. Okay, so here we have z cos square x now will be equal to minus 2 tan x. Then here we have plus c. So it therefore means that at this point, the value of our z, yes, the value of our z, remember we said z, or let's pick it this way, let's divide through by cos squared x. Yes, or we can just leave this like this. This is the same as saying z cos square x is equal to c minus 2 tan x. So at this point, z will be equal to the value of z. We say let z be equal to, let's look at this, let z be equal to y raised to the power of minus 2. So it means y raised to the power of minus 2 cos square x is equal to c minus 2 tan x. So it therefore means that 1 all over y square cos squared x will be equal to c minus 2 tan x. So when you multiply through by y square, yes, when you multiply through by y square, we'll have it as cos square x will be equal to y square in brackets. Here we have c minus 2 tan x. Now we can stop here. Yes, there are other ways you can express this. Yes, if you like, you can divide both sides by cos square x. Then you make this y the subject. Yes, but here we want to stop here. So these are example 1. Yes, this is example 1. We are going to solve another example. Yes, we're going to solve another example. Yes. Now let's call this example 2. Let's call this example 2. Yes. Now the second example is the y all over the x. The y all over the x. Yes, the y all over the x minus 2y tan x minus 2y tan x. Yes, 2y tan x is equal to y square is equal to y squared tan squared x. Tan square x. Now this is another example. Yes, this is another example now of Bernoulli's equation. Now remember, if there is no y square here, there is no coefficient here, it is a linear differential equation. And because of the y square there as the coefficient of tan square x, yes, it is now a Bernoulli's equation. So solution. Now the first step is to divide through by the coefficient of tan square x. It means we're dividing through. Yes, we divide through by y square. Yes, when you divide through by y square, we have 1 all over y square, the y all over the x, minus 2y all over y square tan x is equal to y square tan square x all over y square. Yes. Now the whole of this y square will cancel this y square. Yes, and there will be left with tan square x. Now, this 1 all over y square is y raised to the power of minus 2. Then here we have the y all over the x minus, now this y will go with one of these, so we'll be left with 2 all over y here. Then here we have tan x, now it's equal to tan squared x. Yes, now this is the same as saying y raised to the power of minus 2, the y all over the x minus 2y raised to the power of minus 1. Then here we have tan x is equal to tan squared x. Yes, it's equal to tan squared x. So it means here, we'll just pick this value. We'll say let z be equal to y raised to the power of minus 1. Yes, let z be equal to y raised to the power of minus 1. So if z is y raised to the power of minus 1, it means the z all over the x. Now we are differentiating with respect to x. Now when you differentiate this, it gives you minus 1y raised to the power of minus 2. Yes, then we have the y all over the x. Yes, because this is an implicit function. Yes, so it means in this case now, let's look at this. Let's look at the whole of this now. Let's call this equation 1. Yes, if this is equation 1, now let's look at this. Now we want to express this in terms of this the z all over the x. And if you look at this now, already we have y power minus 2. Look at it here, y power minus 2, the y all over the x. So what is missing here is this minus 1. Yes, so now we're going to multiply equation 1 by minus 1. Yes, we're going to multiply equation 1 by minus 1. So multiplying equation 1 by minus 1, it means here we're going to have minus 1y raised to the power of minus 2, the y all over the x. Yes, minus. Now remember we are multiplying through by minus 1. So if you multiply this minus by this minus here, it will change the plus. So here we have 2 y raised to the power of minus 1. Then here we have tan x is equal to minus tan squared x. Yes, minus tan squared x. So at this point, if you look at this now, the whole of this now is now in form of this the z all over, is now the z all over the x. Yes, it's the z all over the x now. It means this will change to the z all over the x plus 2. Now let's see y raised to the power of minus 1. Look at this here. We said let z be equal to y raised to the power of minus 1. So it means this will be 2z. Then here we have tan x is equal to minus tan squared x. Yes, minus tan squared x. So at this point, the value of our p, yes, p will be the coefficient of z, and the coefficient of z is 2 and tan x. So it means we have it as 2 tan x. And here our q is this. So that will be minus tan squared x. Yes, that will be minus tan squared x. Now in this case, remember we said the equation now will be, yes, the equation will be z times the integrating factor will be equal to integral. We have q times the integrating factor, then we have the x. So it means what we need now is the integrating factor. So to get the integrating factor, our integrating factor is e raised to the power of integral p dx. Yes, e raised to the power of integral p dx. Now remember we said our p is 2 tan x. Yes, p is 2 tan x. So it means here, let's see the value of our integral p dx. Now integral p dx will be integral 2 tan x. Then here we have dx. So this is the same as saying 2 integral. We have tan x. Then here we have dx. Yes. So there we have dx. So it therefore means that here, yes. So it therefore means that here we have to integrate this now. So it means integral 2 integral tan x dx is the same thing as 2 integral. We have sine x all over cos x dx. Now in the first example, in our first example, we actually saw that when you integrate this, it will give ln minus cos x. Yes, ln minus cos x. That's the integral of tan x. Ln minus cos x. Yes, ln minus cos x. Okay. Now let's take it again. Let's do it. Let's bring it out. Let's bring it out. Now when you integrate sine x all over cos x dx, now at this point let u be equal to cos x, so that the u will be equal to minus sine x dx, and the x will be equal to the u all over minus sine x. Yes, so this now will be integral sine x all over u. The value of the x now is du all over minus sine x. So this will go with this. So we left it minus integral 1 all over u. Then here we have the u. So that will give us minus, when you integrate 1 over u, is ln u. So that will give us minus ln. I remember the value of our u is cos x. So here we have cos x. So it means 2 integral tan x dx will be equal to, we have 2 in brackets minus ln cos x, and that will give us minus 2 ln, here we have cos x, minus ln cos x. So at this point, yes, remember logarithm, yes, the laws of logarithm. So it means the 2 now, this 2, we can take this 2 to the other side of the power. So it means this will be, this is the same as saying 2 integral tan x dx will be equal to, we have ln cos x all raised to the power of minus 2. And this is the same thing as saying we have ln, yes, ln 1 all over cos squared x. Yes, because cos x raised to the power of minus 2 is 1 all over cos x, and that will give us cos square x. So here it means the whole of this value now. Let's look at this now. Yes, z times the integrating factor. Yes, so z times the integrating factor. Now, okay, the integrating factor, let's look at, we only got the value of integral p dx. Now let's see the integrating factor. The integrating factor will be e raised to the power of integral p dx, which is the same as saying e raised to the power of ln. Now let's call it log in bracket 1 all over cos square x. Yes. So now this will go with this. Yes. Yes. Remember we said m raised to the power of log x base m is equal to x. Remember this law. Yes. In our class on logarithm, we said m raised to the power of log x base m is equal to x. So of log this base e will give us 1 all over cos squared x. Yes, 1 all over cos squared x. So it therefore means that the integrating factor if, yes, remember we're using if to designate the integrating factor. So if is 1 all over cos square x. It means at this point, let's bring out this z times the integrating factor will be equal to integral q dot the integrating factor or times the integrating factor. Then here we have the x. Now here we have z times integrating factor now is 1 all over cos squared x. Now it's equal to integral. Now the value of our q, remember the value of our q here, we said, where is it? The value of our q, we said is minus tan squared x. So here we have minus tan square x. Then the integrating factor is 1 all over cos squared x. Yes, 1 all over cos squared x. So it means at this point, we have z all over cos squared x will be equal to minus, we have integral tan, yes, tan squared x. Then here we have sec squared x dx. Now let's look at the right hand side. Yes, let's look at the right hand side. Yes, looking at the right hand side, if you look at this integral very well, closely, you will discover that, you know, when you differentiate tan x, it gives sec square x. At this point, now let's look at this. Yes, let's look at this. So here we have minus integral tan square x. Then here we have sec square x dx. So at this point, let u be equal to tan x. If u is equal to tan x, it means the u all over the x. When you differentiate tan x, it gives you sec square x. Yes, the u all over the x is sec square x. And the u will be sec square x. And here we have the x. So the value of the x will be equal to du all over sec square x. So at this point, the whole of this minus integral tan square x sec square x dx will be equal to minus integral. Now remember we said let u be equal to tan x. So if u is equal to tan x, it means this tan square x now will be u squared. Yes. Then here we have sec square x. Then the value of this dx now is du all over sec square x. Yes. So it means here this sec square x will go with this sec square x. So it means we'll be left with minus integral u power 2. Then we have du. Of course, when you integrate this, that will be minus u power 3 all over 3. Then here we have plus constant. Yes, plus constant. And remember, we said the value of our u is equal to tan x. Let u be equal to tan x. So that will be minus tan x all raised to the power of 3 all over 3 plus c. Yes, plus c. So it therefore means that here, what we have now will be, yes, what we have now will be okay, so what we have now will be z, yes, z all over cos square x, z all over cos square x will be equal to, we have minus tan cube x all over 3, then here we have plus c. So at this point, this is the same thing as saying, let's multiply through by cos square x. Okay, let's multiply through by cos square x. Or here, this z all over cos square x, z all over cos square x, the value of z Remember, the value of z is 1 all over y is 1 all over 1. Sorry, 1 all over y, which is the same as y raised to the power of minus 1. So then here we have sec square x. Because 1 all over this cos square x now will be sec square x is equal to minus tan cube x all over 3 plus c. Yes, plus c. So at this point, we can divide through by sec squared x. Yes, we can divide through by sec squared x. So it means here we have 1 all over y will be equal to, yes, or we can multiply through by y. Yes, let's multiply through by y. So it means sec square x will be equal to, we have y in bracket c minus, we have tan cube x all over 3. Yes, so we can express the value in this form. And remember, I said there are other ways you can express this. So thank you so much for listening. Remember to like, share with your friends rather, and subscribe. Thank you, and God bless you.